Hello everyone. In this video I'm going to talk about making rough schematic sketches of polynomial functions. These aren't going to be extremely accurate sketches, but they will provide a lot of interesting, useful behavior, at least near the x-axis. So our goal is, given a function such as f of x is 2x cubed minus 4x squared plus 2x, we want to come up with a picture that shows where it crosses the x-axis, and also what is the behavior of the function between each of the roots, each of those zeros. So our sketches will only be accurate near the x-axis, that's a warning. And this is sufficient for a few purposes. One is understanding solutions to f of x equals 0, because these are represented right there on the x-axis. And also for small values of c, both positive and negative, we can figure out some more behavior of what the solutions look like. For example, for c positive, we can see that there are 3 solutions when c is small. But when c is small and negative, then 2 of the solutions disappear and there is only 1 solution. This is also useful for solving inequalities. So f of x greater than 0, less than 0, greater than or equal to 0, or less than or equal to 0, because we have all the behavior we need to look at. And so our main tool for all of this will be using factorizations of our polynomial functions into linear terms, if we're able to find one. So not every polynomial has a factorization into linear terms, but if we're able to do it, then the techniques from this video will apply. So with our running example, we can factorize it by pulling out a 2x, leaving x squared minus 2x plus 1, and then maybe we recognize that as x minus 1 squared. Talking about actually how to find a factorization is outside the scope of this particular video. So, some terminology. We will always put a coefficient out in the front. It might be just 1, and that is called the leading coefficient, and it coincides with the leading coefficient of the original polynomial. And then, after that, there's some number of factors, and they're always going to be in the form x minus a constant, and they may have an exponent. The exponent is 1 in this first factor's case. I'm writing this in the form x minus 0 because I'm just being formal, and this is the form of a factor that we are caring about, because with this form we can easily read off the roots. So roots, by the way, are exactly the same as zeros, but roots are the word that people use for polynomials. And zeros, of course, is also known as an x-intercept. And also in this form we can read off their multiplicities. So let's look at this example. So I've written the factorized form. So a root, remember, is a 0. So just for sake of solving it so that we can all see why we can read off the roots, as I'm going to show you, let's solve this. So remember, if you have a product of factors that equals 0, then to solve it, you just need to know when any one of the factors is 0. So 2 is never 0, and then the other factors are x minus 0 and x minus 1 twice if you want. So, and a motto maybe is, for a product to equal 0, a factor must equal 0. So we need either x minus 0 equaling 0 or x minus 1 equaling 0. In the first case, we can solve that x is 0, and in the second case, we can solve that x equals 1. And so the roots are 0 and 1. So why have I been writing this x as x minus 0? Well, the point is that in this particular form, whenever you have x minus a number, that number is one of the roots. So x minus r means that r is a root when it's in this form. And also, I should say that if you were to see a term such as x plus 3 inside of a polynomial, then this is x minus negative 3. And so, in that case, negative 3 is a root, not positive 3. So just be careful for that. So, multiplicities of the roots for our running example. What you do is, for each of the roots, you count the number of x minus r factors. So you simply look at the exponents, and also remember when there's no exponent, it's as if there's an exponent of 1. So for root 0, that's the x minus 0 term, and the multiplicity is 1. There's no exponent. And for root 1, that's the x minus 1 term. We look at the exponent, and that is 2. So we've got roots 0 and 1 with multiplicities 1 and 2 respectively. So we've talked about roots, we've talked about multiplicities, and so I'm going to tell you about 3 big ideas that go into the schematic sketches of polynomial functions. Big idea number 1 is that polynomial functions are continuous. So between roots, the graph can't jump across the x-axis. Here's an example of something that cannot happen. We've got our x-axis right here, and we say we've got 2 consecutive roots depicted as such. The function can't cross the x-axis and then discontinuously jump across the x-axis and pick up from the other side and cross again. What would instead need to happen is that the function would, for example, continuously then cross through in the opposite direction that it was crossing, for example. Big idea number 2 of 3. For very large values of x, and that's positive or negative large, so large in magnitude, the leading term dominates. So let's look at this by way of example. For large values of x, our function that we have been looking at is approximately equal to 2x cubed. And the reason for this is that for very large values of x, like for example, say x is 1,000, x cubed would be a number with 9 zeros. So I suppose that is 1 billion. And x in this case would be 1 million, and x would be 1,000. 1 billion is I probably got those exact numbers wrong, but the point is this is a number that has 9 zeros. This is a number that has 6 zeros, and this is a number with only 3. And so this term is the one that is like if you put it into a few significant figures, only that term is the one that matters. Which is to say, graphically, if we zoomed way out, the graph would look just like 2x cubed. And we don't have to care about and the rest of what's going on would just be focused very near the origin. Okay, and the point of this is that then we know what is the behavior of a polynomial function when x is far away from the origin. So in this case, we know that when x is very positive, it is increasing and positive, and when x is very negative, it is decreasing and negative. And finally, big idea number 3, for x very close to a root, the x minus r to the k term dominates. So the factor just corresponding to that root r is the one that matters. So let's see why that is. So for x near 1 in our example, where the roots, remember, were 0 and 1, so when x is very close to 1, one thing that we can do is we can approximate the other terms by plugging 1 in for x, leaving the x minus 1 term alone. Because if x is very close to 1, like say 1.000001, then if we take the x minus 0 factor to 3 significant figures, for example, 1 minus 0 is a good enough approximation. And then if we do that and make that approximation, then we're left with 2 times x minus 1 squared. And so what that gives us is this approximate graph that works for x near 1. And remember, x minus 1 squared, this is the graph of x squared shifted 1 unit to the right. And the 2 out front scales that by a factor of 2 vertically. And so the graph looks just like a parabola, stretched out vertically by a bit. If this were negative 2, the graph would be flipped over, but in this case it's just x squared looking, and it's centered at 1. For x near 0, we can do the same procedure. For the factors that are not x minus 0, we can plug in and this should say approximately equal to, not equal to. It's approximately equal to this function setting the x to 0 in all the other terms, and so it looks like 2x when we are near the origin. So the rule, to summarize, is if we want to know what the graph looks like near a root r, we plug r into all other factors, leaving the x minus r factor alone to get an approximation of the function at that position. So putting these together for f of x's our running example, we can get this rough sketch. So how do the three big ideas play a role here? One is that it's a continuous line, so no jumps. Two, zoomed out, we see that it looks like this x cubed function, or 2x cubed. Yeah, it looks like that. And then for 3, near the roots, we got at 1, it looks like this quadratic, this little parabola, and at 0, it looks like a line, and it's all connected up. And so that is how you make these schematic sketches. So, some tips. These are for understanding what it looks like near roots for different multiplicities, and this is where the multiplicities of the roots come in. So for an x minus r factor with multiplicity 1, this is a sort of special case. It looks like a line when it passes through the root. So you don't know ahead of time whether it's going to be going up or down if all you know is the multiplicity, but it's going to look like one of those two. And then after that, for larger multiplicities, there are basically just two cases. The first case is when the multiplicity is even, and the second case is when the multiplicity is odd. When the multiplicity is even, then it looks like either a parabola or an upside down parabola, whichever two works to satisfy the big idea number 1, that the graph has to be continuous. And when k is odd, then it looks like a cubic. It crosses the x-axis and it takes a little rest as it goes through and flattens out. And it's either going to go vertically up through or down through the x-axis. So let's try one more example before ending this video. So let's make a rough sketch of the function f of x is -3 times x minus 2 to the 4 plus times x plus 1 cubed times x plus 3. So first of all, let's think about what this would look like for very large values of x. And this is a little trick. So when you want to figure out the leading coefficient, what you can do is you just disregard all of the constants in each of the linear factors. So this is -3 times x to the 4 times x to the cubed times x. And if you put that together, you get x to the 4, x to the 3, x to the 1. 4 plus 3 plus 1 is 8. And so -3x to the 8 is the leading term. And that means for large x, our function is going to look like x to the 8, but multiplied by -3. So it's going to be an upside down x to the 8 function. Next, we want to calculate the roots. When we calculate, so we've got x minus 2, which leads to a root of 2. We've got x plus 1, which is a root of -1, because remember, it's x it's x minus -1, and likewise this is x minus -3, and so we have a root of -1 and a root of -3. And we look at the exponents. We got multiplicity 4 for the first root, multiplicity 3 for the second root, and multiplicity 1 for the last root. And so let's put this all together to make a picture. The first thing is you draw your axes and you plot each of the roots, all 3 of them in this case. And what we know is that you know what? I'm going to redraw this from scratch so that we can do it together. And then you can rewind and see if that is indeed what the right thing was. So let me delete this. And so we've got our x-axis. We know we need to put roots at 2, minus 1, and 3. So let's give ourselves a bit of space. So 1, 2, there's a root there. Minus 1, there's a root there. Minus 2, minus 3. What we know is that for large x, it's negative 3x to the 8. So it's going to look something like this as we go away from the x-axis. What we also know is that, okay, so the root of 2 has multiplicity 4. So that means that it's going to be either a right side up parabola or a downwards parabola. And to satisfy big idea number 1, for it to be continuous, it needs to be a downwards parabola so that we can connect it up. Secondly, let's see, our next root is minus 1. It's good to go through the roots in order. I'm going to go in decreasing order. You could also go in increasing order if you wanted. So for minus 1, the multiplicity is 3. So it's going to look like a cubic, like one of these two. And since the function is coming from below like this, that means it has to be this one so that we can make a continuous line. It's going to cross the y-axis somewhere. We haven't calculated it, but we won't do that here. Lastly, multiplicity 1. So it's going to be a line segment that either goes downwards. Can't be that because we'd have to connect up somehow, and that would be discontinuous because there's no other places that we're crossing the x-axis. So it has to cross through this way, and then we can connect it up. So there you go, a rough sketch of what this function might look like. And so, of course, we have computers. We can make a really accurate sketch, not just a rough schematic sketch. And so let's compare. So I plugged it into a graphing calculator, and one thing that we didn't figure out is what sort of scale the y-axis needed. And so with a little experimentation, I found that at least including up to 2400 was enough to see the graph. But as we can see, over at minus 3, we've got this multiplicity 1 root, which means that it's a line segment that goes through. At minus 1, there's this cubic-like root. At 2, there's this quadratic-like root. And then also, for very large values, we can see that it goes down on either side. So it's kind of like, if we were to smooth it all out, it would look like minus x to the 8. Okay, so that's it for this video. So I hope you learned something about making schematic rough sketches of polynomial functions. And we'll see you next time. Bye.